This is a walkthrough of Ms. Volkening's physics class worksheet friction number 2 for the conceptual physics class. Okay, so it says Alexis and Marco are fighting over a box of chocolate sitting on a table. Alexis is pulling the box of chocolates to the right with a force of 8 newtons. Marco is pulling the box to the left with a force of 7.5 newtons. The box of chocolates has a mass of 0.2 kilograms and a coefficient of friction of 0.2 and is sliding to the right. Notice it doesn't say if the coefficient of friction is kinetic or static yet, but it is sliding to the right. Okay. Draw a free body diagram of the box of chocolates. Remember to include all forces exerted on the box. You may have to come back and add magnitudes after completing. Okay, so we've done free body diagrams before. Remember, you have a dot that represents the object you're talking about. In this case, a box of chocolates. So I'm going to label it with its mass, which is 0.2 kilograms. Come on. There it goes. I need an axis. That's really sloppy. Wow. Come on. Sloppy. Stop being sloppy. Try not to be sloppy. I really should have used a ruler for that, but I don't have a ruler on this program. Okay, then I need arrows. So I've always got gravity. Gravity is always with us, which I can actually get a number for this. Remember that gravity is always mass times acceleration of gravity, so 0.2 times 10 would be 2 newtons. Okay, it is sitting on a table, so that means that there's a normal force. The table is apparently flat. I guess I didn't say that, but yeah, let's pretend. And in this case, where is it? Oh, poop. Sorry, it just went away for a second. Okay. If it's on a flat table, then the normal, and I'm not pulling up or pushing down on it, then the normal force would just be the same as the gravity, so that's going to be 2 newtons. Oh, which, by the way, what is the normal force on this box? Now I know, I can put that there. I've got, let's see, Alexis Oh wait, I talk about Alexis is pulling the box of chocolates to the right, so I've got the force of Alexis with a force of 8 newtons. That's more than 2, so this should be longer than the 2's. And Marco's pulling to the left with a force of 7.5. 7.5. Oop, come on. Oh, come on. There it goes. Okie dokie. Now, I'm going to tell you right now, there's a force of friction too. But that's what I mean by you may have to come back and add magnitudes to this. Because there is also a force of friction. Now, it is sliding to the right, so friction must be to the left. I don't know what the force of friction is yet. I just know it's there and it's to the left. Alright. What kind of friction is acting on this box? Kinetic or static? Well, it's sliding, so it has to be kinetic. Calculate the friction on the box. Okay, friction is mu times the normal force, which is 0.2 times 2. That gives me 0.4 newtons. Make sure which way is it? That is left. Make sure it's on your free body diagram. So there it is. We're good. Oh, I could put, however, the magnitude. Okay, what is the net force acting on this box? Well, remember, net force is what you get when you add everything up. Up and down, I've got 2 minus 2, so that's 0. And then left and right, I've got, let's see, I've got 8 to the right, minus 7.5 to the left, minus 0.4 to the left, because friction, don't forget friction, which means overall I've got, that's 0.1. 0.1 newtons, and I got a positive number, and right is positive in this case, so that would be to the right. Alright, flippy over. Alrighty, what is the acceleration of this box? Which way? Acceleration is what you get when you do net force divided by mass. We just found the net force was 0.1, and the mass, if you remember, was 0.2. If you do 0.1 divided by 0.2, we get 0.5 newtons. If you don't believe me, use a calculator. But really, that's what you get. And which way? Well, the way is the same direction as the net force, which was right. So this is also right. Right. Okie dokie. Change colors. That shows up better. To pull a wagon across a lawn with a constant velocity, you have to exert a steady force. But Newton's first law says that motion with a constant velocity requires no force. Explain this apparent contradiction. Well, the thing is, Newton's first law says that motion with a constant velocity requires no force. That's true. What it really says is object stays in motion with a constant velocity if there is no net force. But here's the thing, you've got friction. You have to fight friction so that the net force is zero, because that is the only condition when Newton's first law actually works. Number 8 is actually the same exact question, just with a different situation. When your car moves along the highway at a constant velocity, the net force on it is zero. Yes, that's true. Why then do you have to keep running the engine? Well, you need the engine to fight the friction. Fight. Oh, I wrote fight up here. That was supposed to say fight friction. You know what, basically, it's the same exact answer as number 7. Okay, which takes less force, to make a stationary dresser start sliding across the floor or to keep that dresser sliding at constant velocity? Explain. Well, it takes less force to keep that dresser sliding at a constant velocity. And the reason is that the coefficient of kinetic friction is always less than the coefficient of static friction. So basically, the force of kinetic friction you have to fight is less than the maximum static friction that you had to break to get it going in the first place. Okay. A large box is sliding fast to the left. Okay, I'm going to draw a picture of this. Oh, that is a bad picture. Hang on. Let's try this again. Floor. Large box. Sliding fast to the left. About to hit a puppy. Oh my god. I don't have any brown. Okay, it's a black puppy. I can't really draw dogs, so it's going to be a stick dog. It's a German Shepherd stick dog with its tongue hanging out. Okay. German Shepherd because the ears stick up. Anyways, it's about to hit this puppy. So, you jump in front of it and push it to the right to try and make it stop. You're a hero. You jump in front of it. Ah! Push it to the right. Okay. Trying to make it stop. In which direction is the force of friction between the box and the floor? So a lot of people want to say, oh, well, it's to the left because I'm pushing to the right. But remember, friction is always in the opposite direction of the velocity. So the friction is actually to the right as well. It's helping you stop that box. Okay, right. This could happen. I'm not sure about, like, the box hitting a puppy, and for some reason that dog is bigger than I am, or as tall as I am, so it's not really a puppy. Or I'm just like a brownie or something, you know, from those movies. Anyway, yeah, that's the end of friction number 2.